So.
Okay, now it's on. Yep. All right, hi again. So today I'm giving 2 talks in a row. So first one about neutron diffraction, and then I'll be giving one about reverse Monte Carlo analysis. So most likely my neutron talk, they're both supposed to be about 45 minutes. My neutron talk will probably be slightly long. My RMC talk will be slightly short, but altogether it should add up to about an hour and a half. So this talk is going to be about neutron diffraction primarily, but I'm also going to provide some comparison with the other types of diffraction you can do with X-rays and electrons, just to give you guys kind of the overall picture of how you can do diffraction. And some of you might know, prior to working at c.l.s, I worked at the Lujan Neutron Scattering Center in Los Alamos National Lab for about 6 years. So was previously a neutron scatterer. So we're going to start off with the big picture of diffraction. So diffraction happens when you get radiation scattering off atoms, and you get interference patterns, and you can tell how the atoms are arranged in the material. And there's 3 types of radiation you can use to do this. You can use photons, which are the X-rays, the wavelength reached in that case. You can use neutrons, and you can use electrons to do this. And these 3 methods are all complementary in that they have specific advantages and disadvantages and different types of instrumentation. And many times you might want to use 2 or all 3 of them to solve more complicated structural problems. So X-ray diffraction I won't say too much about because that's the topic of the rest of this workshop. So when you're using photons to do diffraction, X-rays are the wavelength you're interested in because they have a spacing that's about the same or smaller than the separation between atoms. And the other important thing to note about X-rays is their interaction with matter is moderate. So they scatter kind of strongly compared to electrons and neutrons. And X-ray diffraction is by far the most common because you can produce on a relatively cheaply basis X-rays in laboratory machines using X-ray tubes that consist of an anode material, which is usually copper or molybdenum, though it can be other metals, which you bombard with X-rays from an electron gun. They knock off core electrons, and you get a characteristic X-ray wavelength. And pretty much every big university will have some of these that are available. You can also produce extremely bright sources of X-rays using synchrotrons and free electron lasers, as you've heard here. So the main thing about X-rays is they scatter off the electrons, and therefore they tell you about the electron density in the material. And as such, they're more sensitive to elements that have a lot of electrons. Another feature of X-rays is that because the electron density is diffuse in materials, that they have a form factor. Because when you scatter off an atom, you get some destructive interference from scattering off different points within the atom, and that makes the diffraction pattern fall off as you go out to higher Q. And as I said, they have this moderate interaction with matter. So they interact strongly enough with, you can use small samples, but also weakly enough that multiple diffraction usually isn't much of a problem. You can usually ignore that with so-called the kinematic approximation of X-ray diffraction. And of course, they're the easiest to produce. You can make them in laboratory machines, and you can also get very bright sources and do very fast sub-second experiments using sources like synchrotrons or free electron lasers. But the disadvantage of them is, of course, when you're using powder diffraction, is that light elements can be difficult to locate if they're in the presence of heavy elements because they don't scatter very strongly. That's particularly true of hydrogen. Now, electron diffraction is kind of on the opposite end. So electrons interact with matter very strongly because they interact through the electrostatic force. And they are affected by both the electrons and the nucleus. So the very strong scattering is kind of the advantage and disadvantage of electron diffraction. So with electron diffraction, you use very small samples that are usually single crystal. So what you can do is you can get a single crystal diffraction pattern from a tiny grain in a powder sample. So when you have crystallite sizes that are normally you'd have to do powder diffraction, you can actually get single crystal diffraction data like this. And in fact, you have to use small samples. Your electron beam won't go through the sample. So with electron diffraction, you can get single crystal data on powder-sized samples, which is very powerful. And if you're doing like a structure determination, it can be very helpful for figuring out the space group and the unit cell as a first step. One of the problems with this very strong interaction is that multiple diffraction is significant. And so it's much harder to interpret the intensities of the peaks. So usually you're just doing more of a qualitative analysis of using the peak positions. If you have thin crystals and some simple samples, people have started to work out how you can actually do a full structure determination from electron diffraction, but usually you're not actually using the intensities because of the multiple diffraction issue. And you saw more information about electron diffraction. So use the same instrument that you use for transmission electron microscopy. So you can get both microscopy and electron diffraction off the same point in the sample. And it's very useful for space group determination. You can do other stuff like yields to map out elemental composition. And you can often see very subtle structural features, like these stripes in this material here, that you wouldn't be able to see with X-rays or neutrons. The other disadvantage of electron diffraction is it's not a bulk technique. You're going around looking at individual crystallites, so you're only going to ever look at, if you're very ambitious, maybe a few hundred crystallites. So you need to be careful when you do it that whatever you're studying, the crystallites you pick out are representative of the bulk. All right, so now onto the main topic of neutron diffraction. So the interaction of neutrons with matter is very weak, much weaker than the other two cases. And this is because neutrons primarily interact with the nucleus of an atom through the nuclear force. And as you know, the nucleus is very tiny compared to the size of an atom. And it's a very short-range force. So the chance of a neutron interacting with the nucleus is very small, and neutrons are very penetrating. And you need generally large samples, and you interact very weakly. Some other basic facts about neutrons, of course, as you know, they're neutral. They have a significant mass, but they also have wave-like properties, which is why you can use them for diffraction. They have a magnetic moment, which is important because you can get information about the magnetic structure, and I'm going to go into more detail about that later. Another interesting side note is that they're actually unstable outside of the nucleus. So you never have free neutrons just floating around for very long, like in nature, because they decay into protons and other particles. And the whole topic of how long a neutron lives is kind of interesting. It's about 15 minutes, but it's still an area of active research because people have used different strategies to try to determine it, and they get somewhat different answers that are, so they're still trying to pin down how that is exactly. So this is a kind of a big picture of the types of interactions neutrons will have with matter. And so this is important to keep in mind for understanding everything else we're doing. So at the highest level, you can say the neutrons can either scatter off the sample or they can be absorbed by the nucleus and disappear. Just like with X-rays, you have absorption of the neutrons. And I'll talk more about absorption in another slide. And then we have a number of different types of scattering. So you could have either coherent scattering, which is scattering where the phase of the wave is preserved. And you can have elastic or inelastic scattering, where elastic means you're scattering off of the same energy, or inelastic means that you've given up some energy. And inelastic scattering is actually an important part of neutron diffraction. And you can have all four different combinations of these. For powder diffraction and the techniques that we're mainly interested about in this workshop, coherent elastic is the kind that we want, because that's the type that gives you diffraction data. And these other things are sources of noise that we want to get rid of. So with neutrons, if you're looking at the coherent elastic scattering, this is a chart of the value of the scattering by atomic number. And as you can see, with neutrons, there's no real pattern to it. Like with X-rays, it just increases with the number of electrons in the element. With neutrons, it's kind of just random. And neutrons are, scattering is measured by a cross-section with a unit of barns. So that's just like a big red building on a farm. Same thing. Because I guess the story is that apparently it was a lot larger than they thought it was going to be when it was first measured, so they said it was as big as a barn. Anyway, that's the story I've heard. So a barn is actually still quite small in terms of area. So it's basically, it's not an actual like size of the nucleus, but it's like that the neutron has a probability of scattering off it as if it was aiming at a target that size. Though that doesn't mean the target is actually that size. More commonly, though, there's a scattering length, which is usually called B, which is related to this cross-section, which is that. And that's what these are, is the scattering lengths in femtometers here. So you can see there's no periodic trend, and it just kind of varies randomly across here. And another important point to note is that this is for the natural abundance of isotopes. So because it interacts with the nucleus, if you have a different nucleus, you get a different scattering factor. So every different isotope has its own nuclear scattering cross-section. And generally the tabulated values are for the weighted average of the natural abundance. But if you intentionally use a different isotopic composition, you'll get a different scattering factor. And that can be useful in certain cases, as you'll see. Another important point to note that's been mentioned, I think, in a few other talks briefly, is that this actually goes below 0 and you can get negative ones. And I'll talk more about that in a second. So when you're scattering X-rays, you always get a phase shift in the X-ray. And so the waves that scatter have a certain phase relationship. When neutrons scatter, there's usually a phase shift, but sometimes there's not, which means that sometimes when neutrons scatter, they are out of phase from the other neutron scattering off other elements, and that means you have a negative neutron scattering length. And this is something that can be very useful in terms that it gives you a lot of contrast. So you can see here manganese is one of those elements with a negative neutron scattering length, and it's with X-rays, you're not going to tell the difference between manganese and iron, but with neutrons, you can tell them apart very well because iron has a large positive scattering length, manganese has a negative one, and so there's a very big contrast. And another interesting point with this is, I think as I mentioned yesterday, if you have a PDF, since the intensity of the peak is proportional to the number of atom-atom pairs times the scattering power, if you have negative scatters, you get negative peaks. So this in the strontium-titanate is actually a negative titanium-oxygen peak. Of course, the manganese-manganese peak will be positive because the two negatives cancel out. So this negative scattering is something that, that can be useful and you should keep in mind. So in terms of doing like powder diffraction and Rietveld refinement, I'm just highlighting a couple of the main advantages of neutron scattering. So one of them is that you can locate light elements in the presence of heavy elements. So this is from an old project I did a long time ago where we had this double perovskite, and we were trying to figure out the tilt system of the oxygen octahedra. And it was a bit ambiguous from X-ray diffraction because the oxygen atoms contribute very little when you have heavy elements like tungsten and lanthanum. But if you look at with neutrons, you can tell quite easily because oxygen actually scatters slightly stronger than tungsten in this case. So it contributes quite heavily to the neutron diffraction pattern. And you can figure out what the tilt system is quite unambiguously with neutron powder diffraction data. You can also tell elements apart that are next to each other on the periodic table that you wouldn't be able to tell. So cobalt and nickel are next to each other. So their X-ray scattering power is very similar. It'd be very hard to tell them apart if you're trying to figure out where they are in the structure, but they have very different neutron scattering power, so you would be able to easily tell them apart. And over here is just an example of a RMC of a PDF I did on this compound with manganese and ruthenium, where I was able to separate out the manganese and ruthenium to oxygen bond lengths based on the very high contrast, because ruthenium has a large positive scattering length and manganese has a negative one. Another important thing about neutrons is the lack of a form factor. So as I mentioned before with X-rays, because the X-ray density is diffuse within the solid, then the intensity drops off. But with neutrons, that's not the case, because neutrons scatter off the nucleus, which is essentially a point object. And so there's none of that internal destructive interference. So here's an example of an X-ray powder diffraction pattern, neutron powder diffraction. I picked these ones because they happen to have almost exactly the same wavelength, so they're comparable. And as you've probably observed, when you have a diffraction pattern with X-rays, as you go up to higher angle, your peaks drop off. Well, that's for two reasons, which are kind of the same thing. So one is the form factor, and the other is the displacement parameter. and which makes it drop off. And they're both basically things that are smearing out the electron density. With neutrons, you don't have that. There's no form factor, so they keep intensity higher. You can see by this pattern, by about 80 or 90, essentially completely flat. With neutrons going all the way up to 160, you still have peaks with significant intensity. So with neutrons, the peaks still drop off because you still have the thermal motion, which causes a drop as you go up to higher Q. But you don't have the form factor in addition to it, so it falls off more slowly. And so neutron powder diffraction, you get peaks of a significant intensity up to higher angles, so you have more information to work with, and also for parameters that are dependent, have a Q dependence, such as displacement parameters, you can get more accurate values from neutron diffraction than you will get from X-ray diffraction. So incoherent scattering can sometimes be a problem with neutron scattering because it doesn't have any structural information. You get this from having different isotopes of an element randomly distributed, or the nuclear spins. They just create this kind of background noise that doesn't contain any structural information, and it needs to be avoided. And so there's no great way to analytically do this, but there's ways to estimate and subtract it. And it's a problem for when certain elements are present and certain ones aren't. Hydrogen in particular has a high incoherence neutron scattering. So absorption is an issue in neutron diffraction. So it's something that varies greatly between elements. So there's a few elements which are considered particularly bad for neutrons because they have very high absorption cross-section. So gadolinium is by far the worst. It has a huge, just enormous absorption. So, and you can see samarium, europium are also bad, and I just kind of list a bunch of the ones in order of the worst ones. So for some of these, you can actually, if you really want to study it by neutron diffraction, you can sometimes do isotopic substitution. So for gadolinium, there's 7 naturally occurring isotopes of it. The absorption is very large for several of them, but there's a few of them which it's pretty small for. So if you can have the money to afford to buy, isotopically purified gadolinium, you can do an experiment with that. The same thing with boron. Boron is often used as shielding in neutron facilities, or not boron, it's pure boron, but compounds containing a lot of boron. But actually, one of its isotopes has a very strong absorption. The other one has almost none. So if you can buy the pure B11, you can do absorption with boron. You can do experiments with boron. And sometimes people do boron with unsubstituted one. They just have to make sure they have thin samples and everything. But you definitely need to check the absorption for your samples before and make sure you're not dealing with one of these troublesome elements here. All right, the next couple slides are just a few notes about particular elements which are commonly, or for which neutron diffraction is commonly used, that I wanted to just say a few specific things about. So the first one is hydrogen. So hydrogen is something that neutrons are very useful for because X-rays are particularly bad at seeing it. Because with X-rays, there's only a single electron, and what makes it worse is that electron is usually involved in a bond, so it's not even centered around the nucleus. It's just kind of diffusely going between 2 atoms. And so you can't really see it. An interesting thing regarding that is when you look at the bond lengths determined by neutron or X-ray diffraction, you actually get different distances. Because neutron diffraction tells you where the proton is, and X-ray diffraction tells you where the center of electron density is. And when your single electron is involved in a bond, then that electron density is not approximately centered on the nucleus like it would be with most elements. So hydrogen is, neutrons are very good for it, but they're also very bad for it. So the good things are it has a negative scattering length of 3.74, so you can easily detect it in the presence of heavy elements. So you can see it. The problem, though, is that it has the largest incoherent cross-section of any of the elements. So with 82 barons, you get a rise to very large incoherent backgrounds. So you can tell where it is, but you're also going to get a huge background from it. Good thing is, though, is that deuterium, which is just a special name for the the heavy isotope of hydrogen with one proton and one neutron, has a much smaller, about 40 times smaller incoherent cross-section. It has coherent cross-section about twice as large, so positive. So a lot of times what people will do when they want hydrogen is they will deuterate their sample so that they can get a nice clean pattern. And sometimes you can also use deuteration for contrast. So some people that are doing small angle scattering in soft matter, where they have two polymers that have about the same total scattering density, they'll deuterate one of them and keep the other one with hydrogen 1, and then they have a strong contrast in the scattering density between their samples, and they can tell them apart that way. So lithium is another element that people often use neutron diffraction for. So it's also one that's both good and bad with neutrons. So it also has a negative scattering length, so the magnitude of it is a bit on the small side. So this is not great because it's kind of hard to see it with both X-rays and neutrons. So you're a little bit out of luck, though usually neutrons are a bit more sensitive than X-rays to it. It also has a moderate absorption, though it's not like a deal killer necessarily. So people do use it, and a nice thing is that you do have the option of doing isotopic substitution. So you have, the one isotope has a high absorption, but the other one is quite small, so you can use pure lithium-7 to reduce absorption. And then some notes about oxygen. So oxygen is great for neutrons. So it has pretty much a negligible incoherent scattering and absorption, and it has a moderate scattering length. So it's very good for finding oxygen in the presence of heavy elements. Also, nitrogen and fluorine are also good. You can also tell the difference if you have like oxynitrides between oxygen and nitrogen, something you can't do easily with X-rays because they have a strong contrast. If you have oxygen and fluorine together, you can't tell them apart very good because both with X-rays and neutrons, they scatter very similarly. So you're just kind of out of luck in that case. You have to use indirect methods like, on valence assignments or something in order to sort those two out. All right, so the other thing neutrons are heavily used for is for determination of magnetic structures. So neutrons are spin-half particles with a magnetic moment, and while neutrons generally interact through the nucleus, they can interact with unpaired electrons because of the magnetic moment on those unpaired electrons. And that gives rise to magnetic scattering. And if you have ordered magnetic moments, then you get Bragg peaks from those magnetic moments from the neutrons. So that's good. One thing to keep in mind, though, is since now you're scattering off electrons, you have a form factor. And because the electrons that are unpaired are generally in the outer shells of atoms, they're very diffuse. And so the form factor is quite strong for the unpaired electrons. And so your magnetic peaks will fall off very quickly with Q. You only have them in the low angles of your diffraction pattern. So I don't know how many people here are familiar with what I mean when I say a magnetic structure. So I just wanted to briefly explain what that is if you're not someone with a background in this so you can understand. So if you have unpaired electrons, then you have magnetic moments in your crystal. And they can, under certain conditions, crystallographically order. If above a certain temperature, all materials will be paramagnetic, which means that the direction of the spins is just randomly fluctuating. But then if you cool sample enough, you can get certain magnetic structures where you have ferromagnets, where they all point in the same direction, antiferromagnets, where they align. And this is just a simple example. There's lots of different types you could have. You also have these ferrimagnets, which are ones where you have spins of unequal magnitude going opposite directions. So it's like an antiferromagnet in terms of the magnetic exchange interaction, but you end up with a net magnetic moment because they don't completely cancel like in a ferromagnet. And so magnetic structure determination is a big thing people do with neutrons. And so this is just an example of something I did a long time ago and kind of the general procedure for how you do it. So what you generally will do is you get a diffraction pattern like the top one here in the paramagnetic state where you have no magnetic ordering. And you have a whole bunch of peaks from your nuclear structure. And then you cool the sample down below the magnetic transition, and then you'll see new peaks appear that I've marked in red arrows. And these are from the magnetic structure. And sometimes, depending on the structure, you can also have additional intensity on top of some of the nuclear peaks as well. And so you can see how these peaks fall off quite quickly. Like in this pattern, they're basically gone by about 30. You only see a couple of them. And from this, what you can do is you can index them with a propagation vector and determine what the magnetic unit cell is in terms of the crystallographic one. So in this case, you get a K vector of half, 0, half, which basically means that the A and C axes are doubled in the magnetic structure compared to the nuclear structure. And you can have all sorts of very simple ones. You can have complicated incommensurate ones where the spins go in spirals and all sorts of other crazy stuff. And I'm not going to get into lots of details on that. But to solve these, you can use Rietveld refinements to solve them basically in the same way you would do a crystal structure, except instead of refining the positions, those are fixed on the magnetic atom, you're refining the direction of the moment. And this is just some examples of magnetic structure, so from things that I solved a long time ago. So you can have kind of simple ones where you just have a simple antiferromagnet. So here you can see this is this box down here is the crystallographic unit cell. And then the magnetic structure, when it orders, expands it into this larger, 4 times larger unit cell over here. And this is an example of a more crazy one where you have 2 magnetic moments. The red is the manganese and the green is the terbium moment. And here you have this incommensurate spiral of moments going along. And another interesting thing, which is kind of a pretty new field, is using neutrons for short-range magnetic order. So just in the past decade or so, people have worked out the math to figure out how to interpret magnetic pair distribution functions. So when you have short-range correlations of magnetic order, that's going to give you magnetic diffuse scattering. And if you are able to pull that out by subtracting the nuclear PDF and figure out the leftover, you can get the magnetic PDF. And then you can start to look at short-range magnetic order. And this is a very interesting topic that can kind of really change the field of stuff like spin glasses and other stuff that that condensed matter physicists are really interested in. So I just wanted to point that out as something that's kind of new and up and coming, and I think it's going to expand a lot in the coming years. Okay, how am I doing on time so far? Okay. I plan to go a little over, so that'll be fine. Okay, so now we're moving on from like the properties of neutrons and the data to talking about how you actually produce neutrons. So the big picture here is that you have 2 main types. You have a reactor-based and a spallation-based source. So the reactor is based on the fission of radioactive elements. It works kind of similar to a nuclear power plant. Usually you're getting like steady monochromatic beams out of that. In spallation, you're using protons to blast apart heavy elements. And usually that's producing a pulse source for time of flight measurements. So this is a reactor source. So reactor sources work kind of like nuclear power, except your goal is to produce neutrons and not heat. So you have a controlled fission reaction. And this is a picture of a neutron hitting a uranium, and then it breaks it up into 2 smaller nuclei and releases 3 additional neutrons. And so if you do that process, you can produce neutrons this way, and it produces a steady supply of them. Yeah, I guess that's the basics of that. All right, so you have a powder diffractometer on a reactor source, and this is a picture of the BT1 diffractometer NIST, which is the first one I ever used. So these are kind of more similar to synchrotron beamlines, that you have the same sort of components. So you have a neutron source, so you have a flux of neutrons coming in, and you'll have a single crystal monochromator selecting a particular wavelength, and then you collect the diffraction pattern as a function of angle. In this case, they have, because neutron flux is a lot weaker than X-ray flux, they have 32 detectors here that they only have to rotate about 5 degrees to cover a space from about 0 to 160 degrees in 2 theta. Now, spallation sources are a little different. So spallation is the process when you take a highly energetic particle, usually a proton, and you blast it into some heavy element and basically blow the nucleus up into lots of pieces. And when you do that, you release a whole lot of neutrons. So this is a picture of the LANCE accelerator at Los Alamos National Lab where I used to work. So it's a long linear proton accelerator. And what you can do with this is accelerate the protons very fast near the speed of light. And you make them by stripping electrons off hydrogen. And then you hit, they hit a tungsten target. I think in other places they're using now mercury for higher sources because it's liquid and I think it makes cooling easier. So after you smash them in, then you break it up and you release a lot of free neutrons. And this is usually done at a rate of hertz. Like here they were doing it at like at 120 hertz, but then they were bunching the pulses for actually sending it into the target at 20 hertz. And so and then you get pulse sources of neutrons from this pulse right here. And most new facilities, I think probably all new facilities that are being built now are spallation. So spallation is kind of the way everything is going because it has some advantages. And I just wanted to point out that this whole pulse thing, study thing is a general rule, but it's not strict. So you can also actually make a steady source of neutrons by having a steady stream of protons. And there's a facility at the Paul Scherrer Institute that does that. I think that's the only one that I'm aware of. So after you make neutrons, you have to cool them down. So it may not be too surprising that once you've blown up a nucleus and released a lot of neutrons, that you release a lot of energy. So the neutrons coming out are very high energy in the mega electron volt range. But for diffraction, we need them to be much slower to have wavelengths that are useful for diffraction. So they go through a moderator. So basically, a moderator is just something that they can bounce around in and give off energy. So it's usually something with a lot of hydrogen. So basically, you have the hot neutron come in, it'll bounce around a whole lot, giving off a lot of energy, eventually find its way out at a much lower energy. And then the energy spectrum that the neutrons come out with depends on the temperature of the moderator. So you can actually control what energies they come out with by controlling the temperature of the material. So when people say, like, we'll talk about hot or cold neutron sources, they literally talk about the actual temperature of the moderator itself. So yeah, these are kind of materials people often use, just like liquid hydrogen or water or methane. And sometimes, depending on how you design your moderator, you don't get all the neutrons don't fully thermally equilibrate. And this is actually important. You have what's called these epithermal neutrons, which escape before they've come to thermal equilibrium with the moderator. And these are actually important for PDF in producing, getting the high Q data, because they have a bit higher energy there. So I wanted to mention what time of flight is, because it's a little bit different than what you're used to if you're normally doing like diffraction on a lab instrument or a synchrotron here. So this is Bragg's equation, which is hopefully familiar to everybody. So when you normally do diffraction, you're using a fixed wavelength, and you're varying the angle to find d-spacings where you have constructive interference. Of course, that's not the only way to do it. The other way is to have a fixed wavelength and vary or have a fixed angle, and then vary the wavelength to find d-spacings where you have constructive interference. And that's what time of flight does, is you have detector banks that are at fixed angles, and you're getting a spectrum of wavelengths. So when you get a pulse of neutrons out, they have a range of different wavelengths. And you're going to sort them by the time that they arrived to figure out what the wavelength was. So because neutrons, unlike photons, have a rest mass, depending on what energy they are, their speed varies. So the higher energy neutrons will reach the detector first. And by knowing when your pulse hits and you produce the neutrons and timing it well, then you can figure out when the neutron hits the detector, you know what wavelength it was. And so you're actually sorting out the wavelengths by this. So you get a plot of basically time versus intensity, which can then be converted into d-spacing. And you can, since the detector is at fixed angles, you could have banks of detectors at several different angles that are covering different d-spacing ranges with different resolutions as well. So this is normally done at Spallation Sources. You could also do it at a reactor source by putting a chopper in to create pulses of beams, but usually it's done there. So this is just a basic little cartoon I made it. So you have a proton beam, it will come in, hit a target, you have the high energy neutrons go through a moderator, and then they go on a flight path, and they separate out by by energy. They hit the sample, and the detectors record when they hit, and they know what wavelength they were. So what this means is that you have a trade-off between intensity and resolution, because based on how long your flight path is. If you have a short flight path, you have more intensity because the intensity will fall off. These neutrons aren't really being focused. They're just, you're getting the ones that happen to be essentially parallel. But the longer you make it, the better resolution you get, because the neutrons have more time to sort themselves out by their energy, so they can spread out more. So if you have a long flight path, you have high resolution but lower flux, and a shorter flight path, you have high resolution but worse flux. Another thing to point about time of flight data that I think a lot of people don't realize at the beginning is that the pulse is not have an equal distribution of energies, right? So there's a peak at it, and what you get is actually, this is the kind of raw data you get. So you'll have this orange line is roughly the shape of the pulse. So if you think of this in terms of energies, it goes up and then it goes down like this. So this is your raw diffraction data, and you can see that at certain energies, you have a lot higher statistics than at lower energies. So what we'll do is usually people will measure like a vanadium rod because it has a very small coherent cross-section, but a reasonable incoherent one. And you can measure the distribution of energies in a pulse, and then you normalize by that. And so this is what you get for the normalized pattern. But it's important when you're analyzing this data to realize that certain regions of this have much better statistics than other ones. So the data over here is determined with very high statistics. Well, like these big peaks over here actually are not that well known because they're actually smaller peaks. So the error on this is a bit higher. So that's important when looking at looking at the fit of your data to understand which regions have good statistics and which ones don't. And as I mentioned, you can also have a series of different detector banks at different angles. So this is from Nomad data at Oak Ridge. So if you have high angle ones, then you cover down to small d spacing and you cover with high resolution, but you're missing the high d spacing data. And then as you go to lower energies, your resolution gets worse and you lose some of the very small d spacing, but you get higher d spacing. And so you can get a range of d spacings here. And like this part, like in this detector here, like say this peak at 1.6, will have low statistics in this one, but high resolution. But then over here, like this bank, it'll have lower resolution, but higher statistics. So you get kind of the best of both by using multiple banks. And then another thing to keep in mind is the time of flight peaks have an odd shape. I'm not going to get into that. I think Bob actually already talked about that in more detail than I previously understood it. So, but yeah, so when you're getting neutron data, you're often getting these different banks and you can refine them all at the same time. All right, so I'm almost done with this talk. So this is just a few practical aspects about conducting a neutron experiment, things you should know before you do it. So neutrons are very penetrating because they don't interact, so everything's bigger with neutrons. Usually you need a lot more sample than you would for X-rays. All the equipment is big, so everything is big. You're usually going to put your sample in a vanadium can because vanadium has a very weak coherent scattering, so you don't get you get very small Bragg peaks out of it. Because neutron flux is a lot lower than X-ray flux, your collection times are usually several minutes to several hours, where, you know, things that you could do in a few seconds with X-rays, you're going to take minutes to do with neutrons. And then also, a lot of elements will absorb neutrons and become radioactive, so usually you can't get your samples back right away. If you have certain elements, you'll never get them back. So most neutron facilities have calculators where you can calculate the attenuation and how long it'll take for your sample to cool off before you can get it back. So you should keep that in mind when planning experiments. And one last thing I want to mention real quick is inelastic neutron scattering. So this is not something I'm going into more a lot because it's not really the topic of this class and it's not something I know that much about, but it is a major use of neutrons, so you should have some awareness of it, and I should mention it at least briefly in a neutron talk. So neutrons are useful in that they have energies that are kind of similar to the phonon energies in materials. So when they inelastically scatter, that inelastic scattering can be a few tenths of a percent to a few percent of the total energy of the neutron, because they're much lower energy than X-rays. Where X-rays, it's a very tiny fraction of energy usually lost with X-rays. So they're much more useful than X-rays in determining the dynamics of materials. And people use this to measure things like phonons and magnons and other excitations. And they use this dynamic structure factor called S of Q omega, which is sort of like a master equation for condensed matter physics, because it tells you everything about where the atoms are and what they're doing. And so you have this instrument called a triple axis spectrometer, which is basically like a powder diffractometer that also resolves energy. So you have it come in, you have a monochromator, it hits the sample. Then afterwards, you have a crystal analyzer, which tells you, which you can scan with, which tells you not just what angle they're scattering at, but also what energy they are. So you can tell the angle and the energy that they are. And so this takes a while, but you get a lot of information from these kind of measurements. All right, and so neutron facilities, this is just a list of some of the ones in the world. So in the US, there's NIST has a reactor source. Oak Ridge actually has two different neutron sources. It has the HIFER, which is a reactor source, and the SNS, which is a high-power spallation. In Europe, we have the ISIS facility in England, and the ILA reactor in France. And the European spallation source is, I believe, just finishing construction now and will become the most powerful source. So that's something to keep in mind. There's also one in Japan. Canada currently does not have any neutron sources. There was one at Chalk River, but it was shut down a bit ago. But so we have to go to foreign ones. But the Canadian Neutron Scattering Community is still active. So there's this organization, the Canadian Institute for Neutron Scattering, which I'm a member of, is currently working to get organized and provide formal deals with foreign facilities for access to it. So if you're interested in neutrons, I suggest checking out this site here. Okay, and I'll just leave this take-home message slide up and take any questions about neutrons.
Questions for Graham?
Sure.
Oh, that.
So, with preparing a sample for neutron scattering, because of issues with how you can have effects due to different isotopes, how isotopically pure does your sample need to be to avoid any complications?
Well, I guess it depends. I mean, usually people are just using natural isotopes because isotopes are really expensive. But if you're using just to try to get rid of the absorption, I mean, it depends how different the isotopes are, and as long as you know what they are, like if you use like a 90%, 10%, as long as you know that's what it is, then you could accurately calculate what the real scattering factor should be. It depends how bad it is. Like if it's boron, it's not going to be, if you have a few percent of the absorbing one, it's not as bad. If you have gadolinium, then of course, even if you have like 1% of the super absorbing isotope, it'll be a big problem. So it would depend.
I have a small comment. The most common isotope is up to fusion, of course, is deuterium gold. Okay? And that's okay, but the difficulty is that remember the deuterium atom weighs twice as much as hydrogen. So its chemistry is sometimes slightly different.
Mm-hmm.
So it's really difficult to make the assumption that deuterium is not. Looking at phase changes, they will occur in different places, and some phases for deuterium go through hydrogen and vice versa. So beware.
So yesterday for PDF, you said that with X-rays you get to 25 or 30 Qmax.
Mm-hmm.
How is it for neutrons?
So neutron PDF, you can usually go out to higher Q. Usually about 30, 35 is pretty typical. And that's largely due to the fact that you don't have a form factor. So you're not dividing, because you're blowing up that high Q region by multiplying by Q and dividing by the form factor with X-rays. With neutrons, you don't have to divide by a form factor, so you get better intensity out there. And so it's easier to get the statistics you need, despite the fact you have lower flux.
In basis of what should I decide to use reactor source or pulsed neutron?
So for at least in terms of diffraction, I'll just speak to diffraction, because there's lots of other neutron techniques. besides diffraction. But if you're doing just regular powder diffraction, a reactor source is usually sufficient for it. If you're doing pair distribution function, you're going to need a spallation source because you need that epithermal tail to get to high enough Q values. So usually a reactor source does not give you a high enough Q value to do PDF with. You can actually use a hot moderator where you have like something where you're getting a higher energy of neutrons out and do PDF that way. So you're not going to have quite as high resolution in reciprocal space, so your PDF will tend to die a little quicker than it would with a spallation source. But there is a beamline at the ILL that uses a hot neutron source to do PDF. So, yeah.
Well,
so you mentioned that when you are changing the flight paths, you can have a better resolution or a better intensity, right?
Yes.
So which one is better, or it depends on the application of what?
Yeah, it depends on the application of what you need. I mean, if you have a very complicated structure with a lot of overlapping peaks, then you need that high resolution. If you have a very simple structure that's going through some in-situ reaction very quickly, maybe the time is more important, and you can deal with having a little bit broader peaks. So it depends on the condition. Like I know at S&S they have kind of two diffractometers. They have one that's pretty close in, more for doing PDF of non-crystalline samples, the Nomad one. And then they have PowGen, which is a high resolution powder diffractometer, but they've also started doing PDF on that one too. So you can do that one. It'll take a little longer, but you'll get your PDF will die off more slowly as well.
so in terms of costs, how do the neutron and X-ray synchrotron spallation sources compare?
Yeah, so in general, neutrons are more expensive. I think probably a little bit of that has to do with building the facilities, but a lot of it is just that you can't crank through as many samples with neutrons because the flux is lower. Like, with the synchrotron, we can do many samples in an hour. With powder diffraction, you can just kind of crank right through them. With neutrons, you can't go through them as much. So neutron time is considered a little bit more valuable than synchrotron beam time. So generally, if you could do an experiment at a synchrotron or a neutron source, you should do it at the synchrotron. And then neutron beam time should be reserved for problems that really can only be solved using neutrons. So it's also important if you're writing a neutron proposal that you say why you have to have neutrons and why you couldn't do it, using lab-based powder diffraction or, using a synchrotron. And there's a lot fewer neutron facilities in the world than there are synchrotrons. Governments tend to like to build synchrotrons because you get more papers per dollar out of them.
Okay. Any more questions? What? Anton, oh, sorry. Yeah.
So you mentioned that time of flight configuration, we have like a set of detectors at different angles, right? And then you can get into refinement of let's say 5 data sets. Do you average the results then, or?
You just refine them all separately.
And then how do you choose which?
Well, you do a simultaneous refinement of all of them.
Oh, okay.
So all at the same time. So just like you can do, so you're refining the same parameters to 5 different sets of data. So like programs like g.c.l.s and everything are set up to do that. I think the original g.c.l.s was made specifically for that purpose. Is that right? Yeah. And so you can add other data sets in, like you could refine against 4 neutron diffraction banks and a synchrotron powder diffraction data set all at the same time. So it's comparing, it's adjusting the variables to all the data sets at the same time. And then when you do stuff like that, you have to think about like how you're weighting the data sets a little bit. But you do it, all of them simultaneously. So it's a single refinement.
Just that there was a question, and you mentioned something that made me remember that. Like, so sometimes, the intensity is going to follow for higher 2 theta, so you could decide and measure for longer a higher 2 theta. Does Jesus know how to normalize that sort of measurement? When in different 2 theta regions, I use different acquisition times.
There is a way to normalize the data. If you think you know what the scale factor is, you can use that to basically provide all the data points by the